Do not try what you are about to see at home.
Well, there's your problem.
In this special series of Mythbusters,
It's almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and ballistics. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On Mythbusters, there's your problem. On this episode,
Somebody order an explosion?
the Mythbusters countdown
In 3.
to some explosive myths
2,
about shockwaves.
1. Bye-bye!
And later, prepare for impact. With 3 more
It's a Tory Pinata.
based on Newton's laws.
I've been waiting for this, you know.
It's Mythbusters in motion
Bring on the explosions!
as the team tests out some freaky physics.
Never get used to that.
The first myth is straight out of the movies. Our heroes trapped on a boat. A bomb set to blow. Facing certain death, they dive into the drink for protection and surface miraculously unscathed. But would that happen in reality? We know how shockwaves behave in air and water. But what happens when one moves from air into water? Will it speed up, slow down, or even be reflected by the surface? There's only one way to find out.
Good day to blow some crap up, huh?
You bet.
Step 1 is to measure how destructive a set amount of explosive is over distance in air, for which the key piece of kit is this.
An Osico rupture disc, basically a calibrated piece of aluminum foil, and over 13 pounds per square inch of pressure, it will burst, telling you that if you were standing where this disc was, you'd encounter physical injury.
Burst discs are positioned 1 foot apart up to 14 feet to see how far a calibrated block of C4 would cause injury.
All right, JD, go ahead and light it. So this is calculating injurious distance of C4.
Wow, that was a rush.
That'll wake you up in the morning.
It definitely has more get up and go than a cup of coffee. The shock front ruptures the burst discs up to 10 feet.
That's our danger zone.
All right, 10 feet. Now it's time for phase 2.
To find out what effect the same airborne explosion has underwater, the guys rejigged their rig to simultaneously monitor a second blast in air and in H2O.
If there's any truth to this myth, what we should see when we set off that explosive is that this burst disc will blow and this one will not.
Okay, take it up.
Well, it's time to put that theory to the test with the same amount of C4 10 feet away from the 2 pressure discs.
Go for it, JD, light it up.
There it goes. This is invigorating.
Good morning.
Now to find out how the burst discs compare.
Two blown burst discs, 2 intact burst discs. Nice.
That's what I call a result.
There might be something to this after all.
It's looking good for the myth. The water does appear to dampen the shock wave and reduce the risk of injury. But they won't know for sure until they go full scale. So it's off to Pit 232 at Arroyo Seco,
It's perfect.
a man-made water hole devoid of wildlife and perfect for what?
Yes, blowing stuff up.
But first, they've got to get their upscale rig in position.
We'll be deploying our rupture disc masts at 5, 10, 20, and 50 feet away from the explosions.
Each has one burst disc above the water's surface, and two beneath, at 5 feet and 10 feet depth.
And if the myth is true, if jumping in the water really can protect you from an explosion, we should find that one of our masts has its in-air disc burst, but the ones underwater intact.
And for an in-depth result, they'll do tests with 50 pounds of 3 different explosives, starting with gasoline.
Fire in the hole! Fire in the hole!
3, 2, 1. Wow!
The platform is gone.
The shockwave from the gasoline destroyed the floating platform. But how did the burst discs fare? At distances of 50 feet, 20 feet, and 10 feet, they're all intact, above and below the water. But at the 5-foot mark, it's a different story.
5 feet away, clean through.
And beneath the surface?
The burst discs are totally intact.
Interesting.
I thought so.
This myth is in good shape, so let's step it up a notch to a powerful explosive called ANFO, which should be a sterner test than the gasoline. And remember, don't try this kind of boom in your own lagoon.
3, 2, 1. Bye-bye.
Whoops. 50 pounds of ANFO almost obliterated the rig entirely.
It's suddenly become a recovery mission.
So they head straight to the farthest marker.
Oh,
It's burst?
it's clean through.
Really?
Yeah.
Well, God, I wonder what it's going to look like underneath.
Yeah, that's the big question.
Both burst discs are burst.
Wow.
Even at 50 feet, water wouldn't save you from 50 pounds of ANFO. Let's face it, not much would. But this myth has one more boom before it's busted. 50 pounds of dynamite.
Look at it go, our little tetrahedron of death. 50 pounds of dynamite. And 3, 2, 1.
Oh, yeah.
That was a thud.
That was more than the ANFO.
The rig has been decimated by the dynamite.
I only see one of our things left.
Yeah.
Salvage operation.
But will the underwater burst discs have suffered the same fate?
It's a hilarious horror show down here. The 5, the 10, and the 20-foot marker are all huddled together.
And their burst discs are all broken, a pattern mirrored above. So how about the 50-footer?
Well, that's clean through.
Underwater, however,
You're gonna love this, Jamie. The 50-foot mast, 10 foot down, the burst disc is intact.
What about the 5-footer?
The 5-footer is also intact. Repeat, the 5-footer is also intact.
Well, that says something really strong about the myth. That's great.
with 2 unburst burst discs underwater, it's a bombshell result. For some common types of explosive, diving underwater really could save your skin, just like the myth. Next, it's back to the set with another shocking movie myth.
What are you looking so excited about?
All right, we are testing a Hollywood movie myth dealing with explosions.
Great. What is it?
It's a bomb-tastic scene straight from the blockbusters. Escaping an imminent explosion, the hero leaps into the air, and the force of the blast gives them a superhuman boost. But are these film physics bang on? Or is this mission implausible? To jumpstart the myth,
All right, Jay, get those legs up.
Carrie and Tori need to establish the average distance and hang time of a regular jump
All right, I'm in the zone.
by an average person.
Well, that was about 16 feet.
Do it remind you of Michael Jordan, all that air?
All right, your average is 16 feet, mine is 9.5.
All right, well, why don't we look at the high speed and see how much hang time we're actually getting?
Hang time is critical. If a blast can propel someone in midair, they need to be there long enough for it to take effect.
You know, between the two of us, we're talking about an average of 12 feet and only half a second in the air.
Yeah, you know what? That is not going to give us much time to get Buster in the air and then halfway through the jump set off an explosion.
So they decide to take a leap and use elite long jumper stats, which average around 27 feet and a second of hang time.
God, I think I'm gonna be sore tomorrow.
Tomorrow.
Luckily, our jaded jocks won't be doing any more jumping in this myth. That'll be down to Buster. All they have to do is give him a boost.
Since Buster can't jump on his own, we need to help him by giving him both upward and forward momentum. And to do that, we're gonna use this nitrogen cannon.
It's going into a blast zone, so it gets its own protective armor.
There it is.
It's beautiful. Cannon in a box.
Then Tori turns his attention to Buster, fitting him with a strategically placed rod that will launch him at the perfect angle.
Oh! Landed it.
Grant dials the cannon up to 1,500 PSI, and Buster is ready to kick butt.
3, 2, 1.
He flies through the air without a care in the world. All right, let's see how far he went.
At 32 feet, Buster doesn't just smash the Olympic records,
He actually smashed into the top of the shelving.
so they dial the cannon back for launch number 2.
1,000 PSI. 3, 2, 1.
I think that's it.
Cool.
At 1,000 PSI, Buster consistently flies around 27 feet. And the high speed confirms a 1-second hang time. Spot on.
That's good enough for an elite jumper. That's good enough for an action hero.
Time for Buster to surf some shockwaves.
So curious to see if this actually works.
Leaping dummies and explosions. I mean, I can't think of anything better.
The nitro cannon is buried to boost Buster 27 feet from ground level.
Couple more digs and we're there.
But to time the jump and blast just right requires a very tricky trigger.
Now this right here is the trigger for the cannon. It's gonna come down a line of shock tube and split in 2 directions. The first one's gonna come over here, that hits this switch, that fires the cannon. The other side of that goes over to the explosive through a delay cap that's gonna delay it half a second to let Buster get to the top of his arc before it fires off the explosion.
Special delivery.
10 pounds of C4 is wired and ready to blow.
Here comes the firing line.
Will the shockwave extend our stand-in stumpman's jump?
Think action hero.
All right, arming in 3, 2, 1, fire.
Wow, that happened so fast.
Yeah.
We're gonna have to look at the high speed to see exactly what happened.
On review, the trigger worked perfectly. Buster's jump peaked just as the shockwave hit. But did he fly further than 27 feet?
All right, what do you got?
27 feet.
So that's a negative on C4.
C4 negative. But it's a high-velocity explosive, which delivers a rapid shock impulse.
So now we're moving on to a low-velocity explosive, ANFO. This should be really interesting.
Will 10 pounds of low-velocity ANFO give Buster more of a heave-ho?
Here we go.
Let's see if he rides that shockwave.
In 3, 2, 1, fire. That was a lot louder.
You can definitely feel that thud. Let's see what happened.
Yeah.
The ANFO packed a punch, and the shockwave is clear to see. But did Buster hitch a ride?
All right, what do we get?
27 feet.
That's it? So he didn't go any farther.
It's the same result again. Despite changing explosive, Buster didn't surf the shockwave.
So far, everything we've tried has failed. That's 10 pounds of ANFO, 10 pounds of C4. Neither one has moved him any further than no explosive at all. So next up,
A whacking 100 pounds of ANFO. 10 times the explosive might sound like overkill, but this is Mythbusters. So it's boom or bust.
somebody order an explosion?
All right, 100 pounds of ANFO.
And in 3, 2, 1, fire.
Dang, that was a big blast. Well,
Nice disc cloud.
yeah.
100 pounds of ANFO had the Mythbusters jumping out of their skin. But did that impressive shockwave send Buster surfing?
We're looking at the same 27 feet. 100 pounds of ANFO and he didn't move at all.
27 feet again. I so wanted this to work.
Well, I guess we got no choice but to call this one busted. You can't surf a shockwave.
You can't surf a shockwave, but can you hide from one if you find the right angle?
Aren't you going to ask me about my costume?
Nope.
The myth is that in World War I, Germans were very precise about the digging of their trenches.
Towards what end?
They thought that when a mortar landed in the trench, the 90-degree corners would prevent the blast pressure wave from traveling too far in the trench. Sharp, sharp corners. That's the story.
All right, earth-moving equipment and explosives.
Sounds like a perfect day.
It's another myth that shakes down to shockwaves. A clumsy corner will supposedly let one sail right past, while a right angle will stop it dead. But will this myth hit the wall? Before they launch full-scale warfare, time for some reconnaissance using 3 small-scale models. A straight control trench,
It's not pretty, but it'll do.
one with crisp corners,
Freaking sexy, man.
and another with careless curves.
That's how you're meant to be. Yes.
Add water, food dye,
Doink.
oil, and a paddle. And you get consistent, measurable waves.
So this is our impulse wave. It is our stand-in for a shock wave. Lights! Isn't that cool? Here we go.
The machine ripples into action, while Adam marks the wave's high and low points
Yeah, I think that's it.
at the far end of the control trench.
Our control was successful. Our wave impulse machine gave us a wave height from top to bottom at the end of the tank of 3/4 of an inch.
Next up, right-angled trench.
3, 2, 1. Huh.
It's a lot larger on this end than it is on this one.
Yeah, that is cool.
The right-angled tank reduces the wave height to 1/8 of an inch from 3/4 in the control. A 75% reduction. So how will the curved corner trench compare?
It looks a little bigger down here.
It does look a little bigger down there. We might have something.
The curved corners reduce the waves compared to the control, but the right angles reduce them more, which suggests those German sappers may have been onto something.
What do you think?
Well, this story's about blast pressure. We need explosives.
Absolutely. That is definitely the next step.
So the guys launch an invasion at Ione, California, to do battle with this historic myth at full scale.
We're gonna go back in time and dig a bunch of World War I trenches and subject them to some enemy fire. It's gonna bring back a lot of memories for Jamie.
In line with their shop tests, the guys dig 3 trenches. The plan is to detonate 25 pounds of TNT, the equivalent of a First World War mortar, in each one,
Coming along nicely.
to see if rigid right-angled trenches dampen blast waves better than sloppy serpentine ones.
What did you do today? I spray painted some dirt. All right, lads, bring on the explosions!
First up, they'll do a control test above ground with sensors to chart the blast at 10 feet increments.
Above ground blast. And 3, 2, 1.
I can feel that.
That was like a refreshing breeze that lasted a very short period of time.
Well, more like a red-hot fireball. But what are the numbers? 20 feet from the blast, and pressure was 39 pounds per square inch. 30 feet, it was 12. And by 50 feet, it had dropped to just 5. So, with a baseline data set, it's into the trenches. First up, the control trench, with 25 pounds of TNT.
In 3, 2, 1.
Wow, that was spectacular.
Spectacular and spine-chilling.
Oh, man.
The control trench has been well and truly trashed. And the sensors tell a smashing story. Compared to the above-ground explosion, the straight trench amplifies the blast pressure. The question now is whether those crisp right-angle corners will dampen it, as per the myth.
This is the trench that the story's all about, the one with the sharp corners and right angles. And based on everything we've seen so far, by the time the blast wave gets to the end of this trench, past all these corners, it ought to be fairly small.
You ready for this?
Right angle, sharp cornered trench.
Yep.
In 3, 2, 1.
Wow!
I don't know, I think there's going to be a crater there.
I think there might be. Let's go look at it.
It's safe to say that at first sight, that entire trench is toast. German-engineered corners to boot. But a closer inspection tells an absorbing tale.
Wow. Dude, check that out.
I think this tells pretty much the whole story, because that's intact. Everything up to that point is not. As you can see, this is the safe end of the trench. The further you go that way, the worse it gets. By the time you got here, there's not so much energy left.
The high speed confirms that the first corners seem to absorb much of the blast, and the data backs that up. At 20 feet, the PSI was 60. At 30 feet, it was 19. And at 50 feet, it was just 7. A big reduction from the control trench. But the myth says that the curved corners of the final trench will absorb a blast less efficiently. It's the moment of truth.
Here we go. This is 25 pounds of explosives in a serpentine soft-cornered trench. This is for real. This is for the money. 3, 2, 1. Bye-bye.
Never get used to that.
Gosh.
In real time, the final result is anyone's guess. The high speed suggests that the blast did pass the first corner and travel well down the trench. But as ever, it all comes down to data.
What do the numbers say?
Check out the difference between the right-angle trench and the serpentine trench.
It's clear that the numbers in the serpentine trench are higher than the ones in the right angle trench.
I think these numbers tell us that this myth is plausible.
So it is.
Now it's time for a bit of the old equal and opposite, as the team tests out some Newtonian conundrums. Data! First up, Adam and Jamie are having a ball.
Go, baby! What are you doing?
An equation.
Go on.
Does one of these plus one of these equal this?
A wrecking ball-sized Newton cradle. That is fantastic.
Ain't it sweet? It's my favorite.
How do you want to proceed?
Well, since this is all about scaling the Newton's cradle effect, there's no need to go stampeding towards the full-on wrecking balls. Why don't we do it gradually?
You mean incrementally bumping up the size of our Newton cradles? Let's do it.
Okay.
First priority is the obvious cheap gag.
You need to stop playing with your balls and get back to work.
Now, Adam can focus on exactly how this desk toy works.
Now, the Newton cradle is effectively an instant lesson in energy transfer. When we bring this up to full-scale wrecking balls, the biggest problem we could encounter is that the energy transfer doesn't work, that when we lift ball 1 of the wrecking balls, it does not send ball 5 like you'd expect a Newton cradle to work. So how are we going to know how we're doing as we scale this up incrementally? This is how. I will pull ball 1 up to this block, which is the exact same distance from ball 1 as this block is from ball 5. I release ball 1. It sends ball 5 a certain distance that I can measure and compare against our subsequent Newton cradles.
Adam releases ball 1, and in a clear demonstration of this cradle's efficiency, ball 5 almost kisses the blue block.
What'd you get?
The energy transfer was surprisingly clean. Ball 5 traveled 98% the distance that ball 1 did.
Wow, only 2% loss after 1 hit.
Yeah,
Why don't we take it up a notch? Next size up.
absolutely. Let's do it.
Using the magic of montage, Adam whips up a 2.5-inch version in record time.
Shall we try it out?
And it's not just the balls that are swinging.
Oh, that's cool.
Adam releases ball 1 before measuring where ball 5 maxes out. And the results are definitely in the ballpark.
Come on, come on, come on,
It
come on,
looks
come on,
like
come
it's
on.
gonna touch.
It's 3/8 away, which is 3%, which means it's pretty freaking efficient. The desktop model, the ball went 98% of the original distance. This is 97% of the original distance. It's scaling beautifully.
Holy cojones! This myth might just work. Let's scale up to 6-inch balls, weighing an eye-watering 33 pounds each.
Wow, that's heavy.
They'll require a heavy-duty stand.
Nice rack.
Time for a trial run.
3, 2, 1.
Nice. That was a good clean one.
The reason this is called a Newton's cradle is because it's an elegant illustration of all 3 of Newton's laws of motion. As each ball collides, it transfers its kinetic energy almost exactly.
All right, Jimmy. Ball 5 went to 94.1% of the distance of ball 1.
Yeah, that's an additional 3% loss.
I'm still feeling pretty good about this thing.
Yeah, still working. So is increasing the mass causing us a problem? Well, we are seeing an increase in losses the more we scale these balls up. But here's the thing, it's not proportionate. These balls are over 200 times the mass of the original small balls on the toy, and yet we're only seeing a total of about a 6% loss. It's not very much.
Dude, this thing is great. What do we do next?
I think it's time for us to go check out a full-size wrecking ball.
Awesome! I was hoping you'd say that.
They're going to take a 28-inch naval buoy and cut it in half. Across the center, they'll weld a 3-inch thick hardened steel plate that should be able to transfer the energy of the swing. Inside the buoy, they'll add rebar and concrete. That leaves just 2 questions. 1, will it work? And 2, are all these ball jokes eroding the scientific integrity of the show? Let's keep rolling and see.
These things are going to get cut in half, and then we're going to weld the plates right down the middle. We're also going to weld structural stuff that we need onto it, like a bunch of reinforcing bars, and the rest of this space will be filled with concrete.
Adam and Jamie's fearsome spheres are taking shape fast.
And off we go.
And while the concrete pour isn't easy,
Slow down.
it's not long before Adam and Jamie
Don, I need you to get the vibrator ready.
have this part of the build in the can.
Oh, messier than I thought.
After a 2-week build, these balls are rocking. But will they be knocking?
Let's move them out.
All right.
Rigging the world's biggest Newton's cradle will require balls of steel in more ways than one. Given their combined weight of over 5 tons, keeping these balls in the air is a serious engineering feat. Once they're safely secured and the test is underway, they'll use a giant pink ruler to measure the energy transfer.
All right, you ready?
I've been waiting for this, you
I
know?
know, me too. The world's largest Newton cradle. Test number 1 and 3, 2, 1. Go, baby! Yes! 1, 2.
3,
Ish.
4.
The pink gauge records the energy transfer from ball 1 to ball 5 at just 45%, compared to 98% for the desktop version. So what's the problem?
So check this out. Even though this is hardened steel, the areas where the balls are impacting have become flattened from the impacts. And it's not just here, it's throughout all of the balls, which means that they're all kind of squashing like hamburger patties. The amount of force here is something on the order of 500,000 times as much as what's happening with those little balls on the desktop toy.
But instead of creating bounce, that energy is being transferred into compressing the balls. They'll try one last time, pulling ball 1 back to its maximum.
2 strings, max pullback. In 3, 2, 1.
It really is now or never. And it's never.
That went quite a ways.
And now it's all done. There goes one of our cameras.
As far as we're aware, this is the largest Newton's cradle that's ever been built. And it is a Newton's cradle because it's demonstrating exactly the same physical properties that the small one does. But as we get larger and larger, it becomes harder and harder to rein in the physical losses of energy in the system, from the balls to the cables to the overhead structure. While it is a Newton's cradle, it's just never going to be as perfect as the little ones are.
This myth's busted. Though if you could build the balls out of something hard enough to withstand all that force, there's a chance it could work. Like many scientific breakthroughs, this next myth was triggered by accident.
Wow!
A specific accident in the compact myth. In the aftermath of that smash, we heard what may have been a mistaken interpretation of Newton's laws of motion.
Both trucks were traveling at about 50 miles an hour when the impact occurred. Now, that's equivalent to a single impact going into a solid wall at 100 miles an hour.
And the fans went nuts. They are revolting. They rose up and they said, no, 2 cars hitting each other at 50 miles an hour is not equivalent to one hitting a wall at 100 miles an hour. It's equivalent to one hitting a wall at 50 miles an hour. They say that you were wrong.
Let's test it.
The theory is because of Newton's third law. Every action has an equal and opposite reaction. So 2 cars crashing at 50 miles per hour is the same as 1 car crashing into a wall at just 50 miles an hour, and not 100. It sounds nuts, but can this counterintuitive argument actually be right?
I want to smash some cars.
All right, then.
Today, your much-needed dose of car crash TV will be coming direct from a collision test facility in Arizona.
Here we are. This is a 1,280-foot-long crash rail. It has a track embedded in it and a cable that pulls a car along that track towards the impact spot.
Inside each unlucky vehicle, Jamie has added some high-tech sensors to measure the force they'll be subjected to.
It's kind of like a black box.
And because the crash is liable to induce, shall we say, shrinkage, they need to measure the car.
Shall we log the pre-crash length?
Sure.
15 feet.
All right, then.
First, they'll test 1 car into a steel wall at 50 miles an hour.
All right, the cable's ready. Come on in.
The track is ready. The Mythbusters are ready. And if the car is having second thoughts, well, it really shouldn't have signed up to be on Mythbusters in the first place.
All right, this is one car into one wall at 50 miles an hour. Take it away.
Okay, Bob, we're ready for roll-off.
As the engines pulling the cable roar, the car gains speed till it's holding at precisely 50 miles per hour. Then, with the cable detached, it's a one-way trip to Rexville, USA.
Oops.
Time to reach for the insurance policy, if you can find the glove compartment.
Yep, it's a car crash, I think.
Yeah, I'd say what happened here is this car here hit this wall. There.
The evidence of that is undeniable. Like a hot dog hit with a hammer, the front of the car crunched up so much, it was a whole 3.5 feet shorter.
11 feet 7 inches.
This car hit that wall at 50.7 miles per hour and took an average of 58 Gs in the longitudinal direction. I'm gonna go out on a limb and say that when we smash a car into this wall at 100 miles an hour, the G load is going to be significantly higher.
With Adam perched on that shaky limb, another car is strapped into the track of doom.
Commence with the 100-mile-per-hour crash.
Like some lemon-hued, ghost-driven chariot of the apocalypse, it reaches 100 miles an hour.
It's going flat out.
And hurtles towards its own date with destiny. That impact crushed the lemon car with such force, it should be in a glass with ice and a cocktail umbrella.
I can't wait to see what the data set says about the G load.
If the data's still intact.
If anything's still intact.
Got good data.
Really?
Yeah, we got a peak on the left side of 140 and a peak on the right side of 230. And we'd normally just average those to get a resultant there.
So the midpoint's somewhere around 185?
185.
That's nice. That's significantly more than, what was the last one, 58?
58.
Data!
Before it was 15 feet. Now it's 8 feet.
So, not only did the G-load triple, the crash compacted almost half of the car. And remember, these two cars were identical. There's only one more test left. Crash two cars together at 50 miles an hour. Will they resemble the 50 miles per hour squashed hot dog? Or the 100 miles per hour crushed lemon?
Bring on the head-on collision.
From each end of the 1,280-foot track, the identical 1.5-ton cars take off. Like tragic, star-crossed lovers, they're pulled relentlessly towards each other. They reach 50 miles per hour.
It's about to happen.
The cables uncouple, and... well, that was quite a kiss.
That was spectacular.
What can you say?
What can you say? That breathtaking finale is the final piece of their physics puzzle.
There's a windshield between them.
It's pretty evident, isn't it?
It really is.
It looks just like the 50-mile-an-hour against a wall crash.
And nothing like the 100.
Nope.
Amazing.
But just to be sure, Jamie's checking the all-important data.
Well, the figures are in. The orange car got 52 Gs, the yellow car got 58 Gs, which, give or take a few Gs, is the same as what we got against a wall at 50 miles an hour.
And the damage data backs up those numbers. both of the cars are virtually the same length as the 50-mile-per-hour wall test at 11.5 feet. Newton's third law, every action has an equal and opposite reaction, holds true. Although the two-car crash at 50 miles per hour doubles the speed, the energy of the crash is transferred to twice the mass, thereby halving it, resulting in a crash that looks like just one car into a wall at 50 miles per hour. So if the laws of motion can crush a car like a tin can, can a speeding bullet sweep you off your feet? Tori, Carrie, and the rest of the team are taking aim at our final myth.
This one is another Hollywood-created myth, and it's the one around a person getting shot and, like, flying backwards.
So the question is, does a bullet have enough kinetic energy to transfer to a person that would, like, knock them back, whether or not they're wearing, like, a bulletproof vest or something, just like we see in the movies?
We've all seen it happen like this in movies. To capture the action without actually shooting someone, Hollywood experts use special stunt techniques, a crane, and a whole tug-of-war team.
It's a Tory pinata.
But to test if blowback like that actually happens in real life, we're going to use real guns and a real, though recently deceased, pig.
This is our harness, basically, that's going to hold the pig up. We're going to put its hooves, dig the hooks into the hooves, and then this will hang from our rig.
I just saw you punch yourself in the head.
Let's hope out on the range with high-powered weapons and live ammunition, things go a little bit smoother.
That's what you want.
It's the carabiner.
That's beautiful.
Okay.
Look busy. Here's San Francisco PD former sniper Alan Normandy with quite the arsenal.
A Remington 700 308 sniper rifle, 12-gauge shotgun, a Colt M4 in .223, Thompson submachine gun in .45 caliber, and an MP5 in 9mm.
The question is, will any of these have the firepower to make pigs fly backwards? The M4 is loaded with a 9mm hollow point bullet.
Lean forward just a little bit, squeeze slowly. There you go.
A direct hit, but the pig barely twitched.
Hardly at all.
It moved a little bit, but that could have been a fly that landed on it.
Yeah.
Let's try Tori with a .45 caliber Thompson. Nope. And Jamie using a .44 Magnum, shooting the same caliber used by Dirty Harry, also has virtually no effect. The bullet moved at 1,300 feet per second, but none of that forward momentum is transferred to the pig. Let's take it up a notch, or 5.
It's the same sort of bullet they use in the M60 machine gun. You remember Rambo in the first movie where he's got that belt-fed machine gun?
Yeah.
This is the same cartridge.
Rambo? Surely a bullet fired by that dude will send a pig packing. But no, this little pig just won't go.
Nope, back on stage. There you go.
With many of the rounds passing right through the pig, some of the energy is being expended in the hillside behind.
I think we're hitting this pig in the perfect spot. I mean, this is where the highest concentration of his mass is. You couldn't ask for better, and it's not moving at all.
Last chance, a massive, solid deer slug fired from a shotgun.
Yeah!
Hey!
Woo!
Got some movement.
Oh, finally!
But the swine didn't fall back, just down.
Yeah, it actually looked like it hit the hip bone, and the legs spread, and then that caused the jostling that pulled it off the hook.
With the pig off to the smokehouse, the Mythbusters bring in long-suffering Buster in a bulletproof vest. The logic being, maybe if the vest can stop the bullet, we'll finally get some blowback.
Nothing.
What about the same shotgun that dusted the pig?
Hey!
Buster drops, but doesn't go back. Why? Because as we know by now, every action has an equal and opposite reaction. So to make the shootee fly across the room, the shooter would have to be thrown an equal distance backwards. It don't happen.
The simple truth about this test is it's about the impact or effect on the target can't be greater than what the shooter's going to feel, because, you know, Newton's laws still apply.
So if he was going to go 10 feet, the shooter would go 10 feet in the opposite direction.
Absolutely.
And the physics also relies on mass. No matter how fast it's going, a bullet just doesn't have enough mass to push a 180-pound pig or a human backwards.